So now maybe I think we can slowly get started with the talk. So I'll stop sharing this one and I'll let who's the first speaker? Yeah, David take over.
Uh, Thanks for inviting me. And let me see. Can you see the screen?
Yes, I can see your screen. I can hear you well.
All right, cool. All right, so I guess I can get started, and definitely feel free to stop me anytime if you have any questions. But yeah, so I'll today present our paper CLaMR, Contextualized Late Interaction for Multimodal Content Retrieval. So this is the work done with my colleagues at UNC Chapel Hill. Um, the motivation is that right now a lot of the online contents are usually multimodal. This means that it's not only consisting of like for text, it also has if we're thinking of videos, it also has like audio, the images from the videos and so forth. And ideally we want to make use of all of that for any kind of models. And specifically, here we're trying to explore what we call multimodal video content retrieval, where relevance of a document. So the document here is not only the text, but again, the video, audio, not everything associated with it. Where the relevance of these documents can be scored not only from like necessarily one particular modality, but it can also come from jointly from different modalities all at once. So this will mean that for the retrievers, they need to dynamically determine which of the modality or modalities best address a given query. So so I guess here's a teaser figure where we show that I think the standard typical retrieval models, at least in the multimodal space, typically encode each of the modalities separately and then tries to aggregate them together, either using the maximum similarities or like a router and all these. But that often is not that effective as what were our approach, where we try to emphasize on the contextualization aspect. Um, so here is what we proposed. It's called CLaMR, which consists of, I think, three main ideas. The first is that what we call contextualized multimodal encoder. This means that we want to encode all the modalities not separately, but jointly. So what you can see on the right side here, the document encoder with the help of the current VLMs and also Omni models now. Omni models being that it not only takes in like the images and the text, but it can also take in audio and so forth. Um, and with the help of these models, we can now encode everything jointly together so that the model can basically make use of all the information in other modalities to better, to have a better representation in our case. And the other crucial part of our method is called contextualized late interaction. So this is basically the idea that's been explored previously first by Colbert, and then it has been slowly adapted to, I guess, the multimodal aspect. The idea here is that to make sort of retrieval both efficient and highly so like fine grained and like have good performance, it first encodes each of the documents and queries separately so that it can be saved in an offline manner. But then when you're actually retrieving it, you are doing this token-wise sort of similarity calculations and then aggregate them together, which is I think here is the sort of the math formula of that. But the benefit of it is essentially that we are doing this fine-grained interaction by calculating the similarities for each token, but only doing this at a later stage in the offline doing the retrieval so that we're not wasting too much compute resource by sort of calculating this for every query and for every document. Um, yeah, and then the last part of our methods is called modality-wise late interaction. So this is primarily used for training to help the model better understand which of the modalities it should attend to. So later on, I will talk about the data set, but assuming for the data, we have a query that we know it's more relevant to one of the modalities, say the video or the audio, and then we can force it to essentially try to assign a higher score for using that correct modalities. And so with all of that, we basically have a retrieval model that can basically encode everything all at once to better leverage contextualization, and then do this fine-grained retrieval module part to get better performance. Yeah, so although we have this idea, we still need a data set that will be help us to better help the model to understand like what modality to attend to. And so we're using multi-event, which is recently proposed sort of news related data sets that consists of YouTube videos and then queries. However, although it's pretty large scale, consisting of 100K videos, most of it doesn't actually contain the queries because the queries are it requires human annotations to do them. It's quite expensive. So they only have one for like a essentially testing. And what we did instead is we want to expand this so that we synthetically generate sort of modality specific queries using GPT 4.1 for the remaining videos. So that's like around 90K videos. And because each of the sort of document consists of like video title, ASR, the OCR, and metadata associated with it, we can actually generate 4 specific queries that target each of the modalities. So this will at the end it yields around 300,000 examples that we use for training. And the way how we generate is essentially that we only let the model or the GPT 4.1 see, let's say, only the video title and ask it to generate a reasonable query that can be used to like essentially we're using the video title to answer the queries and so forth, and we generate those into essentially we'll get 4 specific modality specific queries to help the model understand that if we're taking this whole document and together, if we're only asking this specific kind of queries, it should ideally focus more on the video title part to get like the relevance judgments. And here's some more experimental setup details. Essentially, the first tab we're looking at is this retrieval task where we want to retrieve the correct documents. And we're using the QuenVL 2.53 billion. So this is visual language models where we essentially have to ignore, let's say, the audio from the video, but we're also trying an approach where we use the audio directly raw. And then we show experiments on multi-event, and then also MSRVTT, which is a standard video retrieval benchmark. And then for baselines, we compare that against single modality retrievers, which basically just use the text query with one of the modalities, let's say the title, or with the description, or with the video, and so forth. And we also have multimodality baselines where we combine these using either like some pooler methods, aggregation methods, or like a router. But we also have a strong baseline that we use the same model that we use to train CLaMR, but only using the simple contrastive sort of loss, but with with all the modalities concatenated together. And then we evaluate on recall and DCG, which are like standard retrieval metrics, and we want them to be as high as possible. So here's the big table of the results. Something to highlight is that, first of all, if um, coming from the single modality to the multimodality requires some kinds of like aggregation methods. So we chose either the average, which is the best out of like taking the min, taking the mean and max and all these. And then we also have a strong router where we ask so given this query, which of the modality do you think will be most useful to answer this question? So it will be mostly useful if the queries contains words, signaling words like dog barking, then we know it probably should go to the audio part and so forth. And what we see here is that if we combine all the single modality retrievers, it often results in worse performance just because it doesn't it sometimes gets overshadowed by sort of uh, some of the weaker trained modalities, so it gets often confused. Um, and then if we're using and then the second point is that if we're using the strong baseline of using the port version of it, it actually perform reasonably well compared to the other baselines. So first of all, this is trained, but also this just demonstrates that using the contextualization is really helpful. But then the best performance is achieved when we're using our method. So this is on top of it, just shows that like the late interaction is really useful. Yeah. And then here are just some more ablations that we show that contextualization is important. And then the modality max enforcement during training. So where we try to find the best modalities during training. That also is helpful. And then here are some additional results where we only train on single modalities. They are all performing worse than if we train it jointly on all the modalities all at once. And then also, this is something interesting to keep in mind that if we use the single modality trained models, but we at inference time we show it with all the sort of modalities as input together, it can still leverage this to perform better. So this is interesting, but also shows that like basically it's important to use all the different modalities. And then one additional results that we show is the modality accuracy, where because we during training, we're enforcing that some of the queries are coming only from one certain modality. We want to evaluate how good the model is able to do this. And so we first filter out the human written queries, and then we generate additional ones to have a separate set of queries that we can be sure of that each of the query comes only specific to one of the modalities. And so we can measure the accuracy on top of it. And what we see that CLaMR again performs the best. So that it just tells us that it can also, not only can it select the different modalities more or less correctly, but it can just pinpoint at which of the modality will be important. So that will be also useful from the sort of interpretability aspect where it will just tell us additional information of where the model thinks is important in terms of the modalities. And then finally, we have this downstream task of long video QA. So we use the long video of video via MME and then long video bench. And here the idea is that if we can retrieve the sort of frames better, then the final answer will be also hopefully of a higher quality. And so what we do is we try to compare different sort of sampling methods to extract the relevant frames. So here we have uniform or language bind and our methods, and we can show that selecting better frames that's using all the information that we have can result in better QA performance downstreams. So I think that's a quick overview of the paper. Thank you so much for listening. If you're interested, check out the paper and code for more details. But yeah.
Thank you so much. Thank you for the great presentation of your contribution. So we can probably continue the discussion about this paper after the second talk by Xiao. So Xiao, please feel free to share the screen and present, please.
Yeah, sure. Okay. Can you
Thank
see me?
you. I can see the screen.
Yeah, sounds good. Okay, yeah. So, so today I want to share our one recent paper, TextRegion, that we found that we can directly get some region tokens that they can align with text feature space without any channeling. So with those text region tokens, we can do some interesting downstream tasks, such as the open world segmentation, referral retrieval, or multi-object grounding task. So the motivation is that currently we have a lot of strong foundation models such as SAM or SAM2 that they can provide excellent object mask, but those masks they cannot differentiate the classes for those objects. So they can only segment those images, but without text alignment. And we also have other vision language models or the text image models, such as CLIP. They can offer image level open vocabulary recognition ability. They can do the zero-shot classification or the vision language retrieval task to retrieve the image, but they cannot understand the local regions in one image, so they cannot handle the high-level understanding tasks such as segmentation or the local region retrieval task or the object grounding. So how can we get a free-range solution to combine the segmentation ability from SAM and the text image alignment ability from CLIP to get some detailed understanding for the provided images? So we can use these examples as the illustration of our contribution. So first, we can get the segmentation mask from SAM2, and we can also get the feature maps from those text image models, such as CLIP, CLaMR2, and perception models. So those models, they can provide the vision language alignment ability. And segment models, they can provide the detailed segment mask. The TextRegion can combine those two models together to understand the details for the input images. And this pipeline is totally challenge-free. We are support multiple architectures, such as from CLIP to CLIP2 and perception encoder, and it's a plug and play implementation. So we only need to modify one attention layers, and then we can directly get those region tokens to handle those downstream tasks. So it's a easy implementation, and we can support multiple models. Okay, so then we can go to our method part. I want to first introduce some prior knowledge. We all know that if we want to use CLIP to do the zero-shot classification, we basically use their class token to do the cosine similarity. We compute the cosine similarity between the image class token and the provided text embedding, which means the class token from CLIP, they are meaningful. They are aligned with the text feature space. So here, I want to first introduce how CLIP compute those meaningful class token. If we regard this is the last attention block from CLIP, so we will compute the self-attention. We first compute the attention score that we will project the input X for the last self-attention block. We project it with the attention query matrix, and we also compute it with key attention matrix to get the Q and the K together. We will multiply the Q and the K to get the attention score for that input token. And for the class token itself, we will multiply the attention score with the projected value matrix. So we can get the output class token for the image. So the class token itself, they can compute the similarity with those provided text embedding. However, if we directly use the patch token from the last attention block, and we compute those patch token similarity with the provided text embedding, we will get some weird classification results. So if we first split this image into several patches, and we predict the class label for those patches, we can see that the patch tokens, they can know what objects exist in these images, but the location is wrong. So it seems the patch token itself, they can align with the text, but the location is inaccurate. So what we want to solve here is that we want to realign the patch token or the region token with their related location. So the solution is to change the computation for the class token. We can regard the patch token itself as other class tokens. So the problem for their default setting is that the class token's attention similarity, they will compute the provided class token its similarity with all other patches, which means for this image, if we want to know the class label for this dog, we will compute the attention similarity between these patches across all other patches. However, the similarity between this patch and the water patches, they are totally different. So we cannot consider that. We cannot use those water patches contribute to the patch token for this dog. So what we want to do here is that we only allow the patch tokens to attend to the patches for the provided regions. These examples shows our method part for the mask-based attention pooling. So if we have one input image, we can first get the patch values for these input images. If we directly use those patch values to do the segmentation, we can see that they basically can predict the class label for those patches, but there are some errors for some patches. For example, those red patches, they should be predicted as the grass, but in this example, they predict them as the child. So there are some misalignment for those patches. We want to use the same segment mask to filter out those noise. What we did here is that we first get the segment mask for the target region, and we only allow the region tokens or the query tokens attend to the patches belong to the target region mask. And we simply do the pooling to get the final region tokens. We regard those region tokens as our region level class token. So those region level class tokens, they can replace the image level class tokens to do the zero-shot prediction. This is our framework of the text region. The yellow part is our mask-based attention pooling. So we can first get the value feature for the provided images. And we also have the segment mask for the provided image. We combine the segment mask and the value feature together to get the region tokens. And we can repropagate the region tokens with the text embedding to get their region logits. As the region token itself, they have their relevant region masks. We already know which region tokens they are pulled by which region mask. So we simply assign the region logits with their relevant mask, so we can know the label for those region masks. So those are our high-level methods part. We also have other detailed implementation that if we have a high-resolution image, there are some small regions. Maybe we will miss those small regions if we simply input the original image to our image text models, because they will downsample them to the maybe 225 by 225, and we will miss those small regions. So we have the multi-resolution patch encoding methods. We will first resize the original feature map for this image into a high resolution feature map, and we also crop and resize the image into several small images, and we will encode those small images with our image text models. In this way, we could encode the patch values for those small regions, and the ensembled value feature will be our input to compute the mask-based attention pooling to get the region tokens. Okay, so that's our methods part, and here are the visualization of our zero-shot results. You can see that if we provide the candidate labels for these images, dogs, chair, and floor, we can get a very good segment results. And here are the quality results for our open world semantic segmentation. Trident is published on ICCV 2025, so it's current SOTA open world segmentation method, and they use Dino and SAM together to handle segmentation task. But TextRegion, we only use SAM as the additional models, and we can get better performance compared with Trident. And those rows are the training-based methods. They trained CLIP VIT-based 16 on a lot of training benchmark, but their performance still underperformed TextRegion. And this slide shows the reasoning segmentation results. Reasoning segmentation is that we will use a complex sentence as our query, and we want to ground the target objects for this query. We use this benchmark to show the grounding performance of TextRegion, which means except the semantic segmentation, which want to segment every object in this image. The reasoning segmentation, we only want to retrieve the target objects in this image. So if we input this complex sentence as a query, TextRegion, they can accurately ground the target objects in this image. And the quantity results, we outperform other training-based methods. Okay, so that's all we want to present here. And this QR code is the link to our paper. Yeah, and thanks.